This is Jack Jackson. We're going to now see an application of the Pythagorean Theorem, and that is computing the distance between points in a plane. So we're going to come up with the distance formula. Of course, if you want to find the distance on a number line, what you do is you just subtract the two coordinates and then take the absolute value. So if the distance between, say, these 2 points here and here, since it's on a horizontal line, is just subtract those x coordinates and then take the absolute value. So we call that distance, that change in x, x2 minus x1, call that delta x, and take the absolute value of that. That gives us that green length. Now what if we want to find the distance between these 2 points here, these 2 blue points, x1, y1, and x2, y2? Well, we can bring this straight down and straight across to find this point here, which is x2, y1, and it forms a right triangle. Well, this side is then the absolute value of delta y, this is the absolute value of delta x, and we'll call that distance d. Well, since we have a right triangle, we can use the Pythagorean Theorem that says a squared plus b squared equals c squared. If this is a right triangle, a is absolute value of delta x, b is absolute value of delta y, and c is d. So d is the square root of delta x absolute value squared plus the absolute value of delta y squared. Now, turns out we don't have to worry about the absolute values because two numbers that are, doesn't matter whether it's positive or negative, if it has the same absolute value, when you square it, whether it's positive or negative, it's going to be positive anyway. So we can drop the absolute values. And we see that d is the square root of delta x squared plus delta y squared. That is x2 minus x1 squared plus y2 minus y1 squared, and then square root. Notice there's no shortcut. If we have the actual numbers in here, we first have to subtract to find delta x and delta y, then square, then add, then square root. So for example, the square root and the squares do not cancel each other out. So let's look at an example. Okay, so here's the example that we have. So right now, x1, y1 is at 2, 3. x2, y2 is at 7, 7. Let's make that 8, 7, just to make the numbers different. Okay, and so then delta x is 8 minus 2, which is 6. Delta y is 7 minus 3, which is 4. And so we square the 6 to get 36, square the 4 to get 16. Add is 52, and the square root of 52 is approximately 7.21110. Now, the square root of 52 is the exact value if these are the exact coordinates, and the 7.2 whatever is an approximation. So let's try another one. You try this one yourself. So let me move this around. You can read off of the picture here the coordinates. How about, let's do it like this. There we go. How about that one right there? So read the coordinates from the grid and work out the distance using the distance formula. When you're finished, come back. Press pause now. Well, we're back. We see that this coordinate here for x1, y1 is -2, -2, and this is 7, 1. So 7 minus the -2 is positive 9. We're going 9 to the right. We can just count as well. And this is 1 minus -2 is 3. So we're going 3 up. So we're going right 9 and up 3. Square those, we get 81 and 9. Add those together, we get 90. And then the square root of 90 is the exact answer, or approximately 9.48683. Okay, now we can generalize this to a three-dimensional distance formula. So take a look at this one. Here we have something that's supposed to represent a rectangular box, a prism, right, rectangular prism. And we have the edges here. So we have the blue edge and the green edge. We have the purple, which is going across the diagonal of the bottom face, across the floor there. So we have a triangle here laying on the bottom or the floor of this triangle, of this box. And then we have another triangle cutting up through the middle. So the distance we're looking for is this red distance from one corner to the opposite corner. So first of all, look down here. We take this one, we bring it straight down so that it has the same x and y, but this as b, but the same z as x. or is A. And so we get a triangle then we completed here and bring it back here so that this point has the same X and Z as A, but the same Y as the original point up here. So now look at this triangle here on the floor, you might say, and notice that it has a right angle right here at D. It doesn't look like a right angle here because we're looking at it from up in space looking down. But the length of this side, well, it's the absolute value of delta x, so it's x2 minus x1. This is delta y, y2 minus y1, absolute value for the length. And so by the Pythagorean theorem, or the distance formula that we just did, we get that's the square root of delta x squared plus delta y squared. Now, that's the hypotenuse for this triangle. Now look at the other triangle here. So this one's going up the side here, across the bottom, and then through the middle of the box here. Now this time the purple side, which was the hypotenuse last time, is now one of the legs, but we do still have a right triangle with a right angle right there at C. This vertical length is delta Z, or at least the absolute value of delta Z, and so we use the Pythagorean theorem again to find the length of the red hypotenuse. So we square this side and it cancels, the square and the square root cancel each other out. So this becomes delta x squared plus delta y squared, plus we square this one, delta z squared, and then from there we take a square root to find that distance, and we see that the distance that we're looking for is the square root of delta x squared plus delta y squared plus delta z squared. And notice that this actually generalizes very nicely. For 2 dimensions it was just the square root of delta x squared plus delta y squared. For 3 dimensions, it was square root of delta x squared plus delta y squared plus delta z squared. Actually, for 1 dimension, it turns out to be the same thing as the square root of delta x squared for just 1, because the square root of delta x squared is just the absolute value of delta x, which is the distance formula in 1 dimension on a number line. And we can use this to come up with a Euclidean distance formula for 4, 5, or 6, or however many dimensions. We just take each direction and do the delta x, delta y, delta z, delta whatever letter we have the other directions, square them all, add them all up, and square root. It becomes harder to visualize this once it gets beyond 3 dimensions, but we could do such a thing. So anyway, we have a nice little formula, and it really boils down to using the Pythagorean theorem, or here the Pythagorean theorem twice, to come up with this formula.